Ever imagine, like, technology that can see right through you, not just an X-ray, but something that understands, like the network of blood vessels keeping you alive?
Yeah, it's incredible how AI is moving beyond just identifying simple objects to analyzing complex structures in medical images, stuff we might otherwise miss completely.
Which brings us to today's deep dive, folks. We're going deep into how deep learning is being used for image segmentation, specifically of blood vessels in your lower extremities.
We're taking a look at this chapter, right, from the 2024 ebook called Artificial Intelligence, published by Wissenschaftliche Verlag Le Coutier.
Oh, yeah, I saw that. Dense stuff, huh? Lots of pretty hardcore scientific articles.
Yeah, definitely for specialists, but there are some general insights we can all glean.
Definitely. So today we're doing the heavy lifting for you. No need to wade through the jargon. We'll break down this cutting-edge research and why it could matter for your health.
Exactly. Our mission for this deep dive is pretty clear. To understand how AI is being used to better diagnose vascular diseases in, well, your legs and feet.
Okay, cool. So first things first, why are the blood vessels in our lower limbs so important? The article gives some good background on this.
Right. So the article points out that, blood vessels in your legs and feet, they're critical for delivering oxygen and nutrients to those tissues and carrying away waste products. And when those vessels get narrowed or blocked, well, it can cause some serious problems.
That's what leads to peripheral artery disease, right? I know that can cause pain, numbness, and in severe cases, even amputation. Scary stuff.
Absolutely. That's why early and accurate diagnosis is so important. It's key for managing these conditions and preventing those worst case scenarios. And this research focuses on a pretty specific area, anatomically speaking. It's looking at those blood vessels from where the aorta splits, like down in your abdomen all the way down to your kneecaps.
So we're talking about a whole network of vessels. Before AI, how did doctors assess their health? I know the article mentions some standard methods.
Right. There's the ankle brachial index, or ABI for short. It's a simple test that compares blood pressure in your ankle to the pressure in your arm. If there's a big difference in that ratio, it could suggest a blockage somewhere in your leg.
Makes sense. If there's a narrowing, the pressure below it would be lower. The article also mentioned a more involved imaging technique, right? And one using contrast dye.
Yeah, that's contrast enhanced computed tomography angiography, or CTA. It's where they inject a special dye that makes your blood vessels show up really clearly on a CT scan.
So doctors get a good visual of what's going on.
Mhm.
But even though these methods are helpful, I'm guessing they have limitations. Like ABI is indirect and CTA involves radiation. That's where AI comes in, right? The article talks about how AI is offering a new way to look at this problem.
What's really cool is how AI is changing the whole diagnostic game. And as the article points out, these breakthroughs often come from unexpected places. Algorithms designed for, say, recognizing objects in photos, they can be adapted for analyzing medical scans and segmenting blood vessels. It's like the same basic image analysis principles applied in a totally different field.
It's like bringing in an expert with a fresh set of eyes, right?
Mhm.
Able to spot patterns we might not see. And the focus here is on deep learning for segmentation. What does that actually mean when we're talking about, like, blood vessels?
So image segmentation is all about precisely identifying and outlining the blood vessels in a medical image, separating them from everything else. And deep learning, which is a type of AI, uses these things called neural networks. They learn to recognize patterns from tons of data, then apply that learning to new images. The article focuses on two main types of neural networks, UNet-like architectures and 3D convolutional neural networks, or CNNs.
Okay, those sound a little technical. Could you break down the main differences, in a way that's easy to understand?
Sure, think of UNet like a U shape. It's great at capturing both fine details and the overall structure in a 2D image. So it's really effective for segmentation, like picking out individual blood vessels pixel by pixel in a slice of a scan. Now, 3D CNNs, they process the image in, well, 3 dimensions, so they give a more complete spatial picture. While UNet is amazing at segmentation, 3D CNNs are more versatile and can be used for lots of deep learning tasks, not just isolating objects. So the U-shape is for detail in a 2D view, and the 3D approach provides a more complete view of the whole structure.
I see. UNet looks at slices, and 3D CNN tries to understand the whole thing. The article also mentions something called multi-head attention. What's the advantage of using that?
Oh, multi-head attention. It's a technique that allows the AI to kind of look at different parts of the image in different ways at the same time. Imagine it as having multiple eyes focusing on different aspects of the image. It's different from self-attention, where the AI looks at the whole image from just one perspective. So by analyzing the image from different viewpoints simultaneously, the AI can better understand how everything connects in the vascular network, which leads to more accurate segmentation.
So it's not just seeing lines, it's understanding how they form the whole system from different angles. Pretty sophisticated stuff. But this AI needs something to learn from, right? I know the article highlights the importance of training data.
Absolutely. Deep learning models are only as good as the data they learn from. To segment blood vessels accurately, you need a huge amount of medical images where those vessels are, like, perfectly identified. The article mentions that this data comes straight from medical settings, hospitals, clinics, usually in a format called DICOM. It makes sure all the important info about the scan and the patient is included.
But I imagine you can't just feed those raw images to the AI. You need to do some prep work,
You
right?
got it. Raw medical images need a lot of pre-processing. You got to reduce or remove any artifacts, like irrelevant visual elements that could confuse the AI. Then you need to adjust the images to a consistent size and make sure they're geometrically standardized. Intensity normalization is important too, to adjust for variations in brightness and contrast between different scans. And there are other standardization steps to ensure consistency across the whole data set.
It's like getting the canvas ready before the AI can paint its masterpiece. The article also talked about strategic data augmentation. Sounds like a way to get more out of your existing data.
It is. To build a really good AI model, you need a massive and diverse data set that reflects the variations you see in real medical scans. Data augmentation techniques artificially expand the dataset by creating tweaked versions of the existing images, like adding slight distortions, reflections, or a bit of noise. The article mentions a study that started with 500 images from just 11 patients. Using these methods, they were able to create a dataset of 12,000 images. It's like showing the AI lots of slightly different versions of the same thing so it can recognize the important features more reliably.
Wow, from 500 to 12,000. Like teaching the AI to recognize blood vessels from every possible angle. And then comes annotation, right? Which sounds pretty meticulous.
Annotation is super important. It's where experts use specialized software to, like, manually trace the blood vessels on the images. The article mentions examples from lateral or side views and transversal or cross-sectional views. Basically, they're carefully drawing outlines of the vessels to create a ground truth for the AI to learn from, like showing the AI, this is what a blood vessel looks like in this specific type of scan.
So a detailed map for the AI to learn the territory. Once you have all this prep data, the real testing begins, right? The article talked about different AI models being tested.
Yeah, they focused on unit-like encoder-decoder architectures. These networks have an encoder that picks out important features from the input image, a decoder that uses those features to rebuild the segmented image, and these things called skip connections that let information from early stages of the encoder go directly to the decoder.
What about that bridge made of transformer layers the article mentioned? What's its role?
The bridge. It sits between the encoder and decoder. Transformer layers are really good at figuring out long-range relationships within data. In this case, the bridge helps process and transform the features picked out by the encoder so the model can understand how different parts of the vascular system connect across the entire image. It basically connects the initial high-level features with the detailed reconstruction in the decoder.
So the encoder finds the key elements, the bridge figures out their connections, and the decoder puts it all back together. They tested multiple models on that huge 12,000 image data set, and one called Transinet did really well.
Yeah, the Transinet model was super promising. They used specific metrics and visualizations, like graphs, to see how well each model performed. They also used something called folding or cross-validation. They split the data from those 11 patients into 4 groups, trained the model on 3, and tested it on the 4th. They did this 4 times, with each group serving as the test set once. It's like testing the AI in different scenarios to make sure it can actually handle new data, not just memorize what it's seen before.
Making sure the AI actually learned, not just memorized. The article compared the Transinet model to a more traditional object tracking model, and the results were fascinating.
Yeah, that comparison really showed how much better this new approach is. Transinet accurately identified the whole vascular system in the images. What's really cool is that it also found a thinner vessel in the left leg of the example patient. This could be a sign of something like stenosis, which is narrowing of the vessel, or maybe calcification or fatty deposits.
So it's not just mapping, it's pointing out potential problems. What about the older model? How did that perform?
Well, the object tracking model totally missed that vessel in the left leg, and It messed up on the right leg, too, thinking the artery next to the bone was one big vessel. This really shows how much better deep learning is at distinguishing between those complex anatomical structures.
Wow. One model gives you detailed, potentially important information, while the other misses key details and makes mistakes. The article also mentioned what the researchers want to do next.
Their goals are pretty focused. They want to tweak the AI so it doesn't confuse blood vessels with bones. They also want to improve its ability to diagnose calcifications within the vessels, which is a major sign of vascular disease. And, of course, they want to train their models with even bigger and more diverse data sets to make them even more accurate.
So it's a work in progress, always getting better and better.
Exactly. This research shows just how powerful AI, particularly deep learning, can be for diagnosing vascular diseases.
It's mind-blowing that we have tech that can give us such a detailed and potentially more accurate view of our circulatory system, even picking up on tiny things that could be signs of trouble.
And as the article subtly suggests, maybe seeing all this detail with AI reminds us just how important it is to take care of our health. Our bodies are incredibly complex and, well, there's a lot that can go wrong.
Thanks for joining us for another deep dive. We'll see you next time.
See you then.